Maybe you can go back to just our faces for now. Oh, wow, we have 30 people on already. Great. Awesome.
All right.
We'll just give a couple more minutes for any stragglers to join. I was informed that there is a new link that was just sent out, so if people are figuring that out, it's understandable. Apologies for the confusion. Hello. The stream's current bitrate is, oh, okay, that went away. Never mind. Okay, it's looking like the viewership is stabilizing. Do we want to go ahead and start?
Sounds good to me.
Awesome. So thank you everyone for being here. This is Universe at Home, the stand-in for our usual Universe in the Park program that we do at parks around the Twin Cities area when there's not a virus that is making us all distance ourselves. So I'm Jamie. I'm a graduate student at the Minnesota Institute for Astrophysics at the University of Minnesota. And I study cosmology, specifically the microwave background, the afterglow of the Big Bang, to look for signatures from the beginning of time.
And I am Laura Salo. I am also a graduate student at the University of Minnesota, and I am currently studying the host galaxies of supernovae.
So today we're going to start off with a presentation on the secret lives of galaxies, how they're born, how they grow up, their eventual fates, and all the interesting things they do along the way. And afterwards, we'll have some time for questions before we'll move into our activity for tonight, which is using a service called Galaxy Zoo, which Laura will tell you more about. So I think we can go ahead yeah. Sorry, my window disappeared. Okay, yeah, Secret Lives of Galaxies. So this galaxy that you see right here, this is our own Milky Way. So what is a galaxy, first of all? This is a question that, now you can go Google it, but from early on in people's history, they didn't know what a galaxy was. They didn't know how to tell if they were living in a galaxy. So we'll sort of take a historical perspective here. And that historical perspective is, if you look up in the night sky, then if it's really dark out, you can see this fuzzy band, this Milky Way, hence the name. And from very early times, even 1,000 years ago, Islamic astronomers could tell that the fuzziness was actually a bunch of stars that were just really close together, and they were so far away and so close together that you couldn't really see them as individual stars. So they just formed this sort of smooth band. And this was sort of rediscovered by Galileo, actually, because I don't think Galileo and the Islamic astronomers were sharing notes, unfortunately. But then Thomas Wright and Immanuel Kant, the famous philosopher, sort of tried to extend what Galileo was doing. So they had their telescopes and they looked at the Milky Way, and they also saw that it was made up of a bunch of stars. So at that point, we already knew about our solar system, how we have a sun, the Earth orbits the sun, we have other planets like Mars and Jupiter, et cetera, that also orbit the sun. And so Thomas Wright and Immanuel Kant said, well, maybe there's this thing made up of a bunch of solar systems that sort of works the same way, where there are a bunch of solar systems that are all held together as one big blob by gravity, and they rotate, and we're inside of it. We can go to the next slide. So the discovery of other galaxies was sort of crucial in figuring out that we lived inside a galaxy. So in the 19th century, a rich Irish lord named Lord Rosse built an enormous telescope. There's a picture of it here. They called it the Leviathan of Parsonstown. And he was actually able to see some galaxies. So in the lower right here, we have his drawing from 1845, I believe, of the Whirlpool Galaxy. But he didn't really know that this was a galaxy. He just saw this fuzzy spiral-looking thing that he saw looked cool and drew a picture of it. We can go to the next slide. So we've come a long way since then, just as an aside. On the left is Lord Rosse's original drawing of the Whirlpool Galaxy. But on the right is a Hubble Space Telescope image. And if you copy that text and Google it, or you just look up Whirlpool Galaxy and find this image, it's super high resolution. You can zoom way, way, way in. It's insane. So, obviously we've made a lot of progress in telescopes in the last 150 years, and being able to put them in space is really awesome too. So Lord Rosse had seen these fuzzy spiral-looking blobs, but it still wasn't clear. Did we really live in one of these, or are these just normal nebula that, when a star in our own galaxy dies, it can leave behind this fuzzy cloud? So were they just more of that? Well, this was actually the subject. This was actually the subject of a pretty historically interesting debate. They call it the Great Debate in Astronomy, between these two guys, Harlow Shapley and Heber Curtis, in 1920. They look very 1920s. So Harlow Shapley thought that, no, these things aren't other galaxies. There's no such thing as another galaxy. The Milky Way is just the whole universe. And those spiral things, the spiral nebulae, as they call them, are just small, and they sit inside it. But Heber Curtis, the guy on the right, said, no, the Milky Way is just one of these spiral things that we sit inside of, and these other spiral things are their own island universes, what we would later call a galaxy. So basically a big conglomeration of solar systems, a bunch of stars orbiting each other, orbiting their collective center of mass, each star having potentially its own planets and all sorts of interesting things around it. So one of the reasons that this was such a difficult question is it's really hard to figure out how far away something is in astronomy, because how do you tell if something is really bright and really far away versus really dim and really close to you? It's because we can only look out at the sky, really. We can't travel to another galaxy to make an observation from there. It's really not easy to figure out how far away things are. So that was one of the reasons why people didn't understand early on that these spiral nebulae were the size of, they were much further away than people believed the size of the entire universe was at the time, but they were totally wrong. So around this time, we started to understand and we started to have better instruments and telescopes that let us actually map out things like the spiral arms of the Milky Way and helped us understand that, no, we do live inside of one of these galaxies. And these other ones are, they're scattered throughout the universe. Yeah, so Heber Curtis was right. They both had some things right and some things wrong, but history will remember Heber Curtis as being the one who got the main point right. So galaxies merge a lot when they're, over the course of their lifespans. So there are all of these big blobs of stars and dust and gas floating around that can eventually collide with each other. And this is actually going to happen to the Milky Way and the Andromeda Galaxy in about 4.5 billion years to make a new galaxy that we'll call Milkomeda, if you want. But what you have to keep in mind is that galaxies are really big. The Milky Way is like 100,000 light years across. So that means even a beam of light would take 100,000 years to get from one side to the other. And galaxies are moving they're moving pretty fast, but way slower than light. So these mergers it's kind of happening in slow motion. It's going to take place over hundreds of millions, even billions of years. So, it's not going to be a disaster for us if we're still around in 4.5 billion years. The chances of two stars colliding with each other or something is so low. The distance between stars is just so huge in a galaxy. But what does happen is the big dust and gas clouds will collide with each other. And when that happens, they'll, coalesce and congeal and start collapsing and forming new stars. So you might notice that the two galaxies on the left here and the merger in the middle are bluer than the thing on the right. So on the left, these are spiral galaxies. We'd call these early type galaxies. And on the right, we have elliptical galaxy, which we would also call a late type because it's older. So what happens is all of this gas and dust forms a bunch of new stars, but all of the gas and dust gets used up. And when new stars get made, there's going to be a lot of big, bright ones. And the big, bright stars tend to be bluer. But the biggest, brightest stars die most quickly. So what's happened is all the gas and dust has gone into making new stars, but then the big blue stars all died. So the thing on the right, we sometimes call red and dead, because only the really tiny red stars, ones like about the size or smaller than the sun, that live a lot longer, they're the only ones that are still around this late into a galaxy's life. And just a aside, the giant elliptical galaxy on the right in that last slide is one of the largest galaxies we know about 100 billion, and 100 billion solar masses. So another cool thing about galaxies that affects them merging is supermassive black holes at the centers. So a lot of you might have seen this really awesome image from the Event Horizon Telescope group, where in this main image we have a galaxy that the galaxy is right in the middle there, and those two things on the left and right are actually jets that are coming out of the supermassive black hole that you see imaged in the bottom panel. So the supermassive black hole is spinning and it's spitting out these jets of gas and dust along the poles, along the axis that it's spinning on. And then those jets are hitting the gas and dust that's just in the galaxy and making it light up. But I should just note that the ability to actually look at the event horizon of one of these, even though they're millions of times the mass of the sun, they're enormous objects. This is so far away that it's an incredible technical achievement to be able to actually generate an image of something like this. So here are some artist conceptions of what I'm talking about. At the top, we have two supermassive black holes that are spiraling in towards each other. And so the supermassive black holes will merge when galaxies merge eventually. But this is actually kind of a big question as far as how galaxies form, is how the supermassive black holes grow and evolve, and how exactly the supermassive black holes affect the growth of the entire galaxy. So for example, there's something called the last parsec problem, where we just, if you just put two supermassive black holes next to each other in a box and just let them go towards each other, then they would actually get stuck. There would be some distance where they couldn't get any closer to each other because they just wouldn't be losing enough energy. They wouldn't be able to get any closer. So we think that, obviously a real galaxy is not two supermassive black holes in a box. We can see in these images that there's gas and other stars and all sorts of stuff that we think has to play a role. But exactly how that works is still an open question. So these supermassive black holes can also feed. In that last image, those jets were produced by a feeding black hole. So we call these active galaxies, or active galactic nuclei is the jargony way of saying that. Basically, the black holes are just eating up stuff, and that stuff that they're eating up is getting really hot. So we can see that in this bottom image. The stuff right close to the center heats up because it's just friction rubbing against each other. And then as it's falling in, some of that matter gets shot out along the poles on these jets that you can also see coming out of there. So if you tune in 2 weeks from now, Trevor and Sean are actually giving a presentation on the extremes of space, where they'll talk more about supermassive black holes and active galactic nuclei and all sorts of interesting things that come out of those. But today we're going to be focusing on the galaxies specifically. So this is sort of the lifespan of a typical galaxy. On the very left, we have some simulations of structure formation. So what you're watching is the universe evolve forward in time from the initial state, which was this sort of just hot, dense, soupy plasma that I could tell you a lot about, but not right now. You can ask questions about it later if you're interested. But the gist of it is that all of that smooth matter eventually starts to clump up. And so when it compresses along one axis, if you have a blob, it compresses along one axis and can form a filament. And then it compresses along the other axis to form a blob, which becomes a galaxy. So we can see these filaments starting to form. And then eventually where the filaments intersect, we get clumps that become galaxies. So all of this primordial hot, dense matter clumps up, stars start forming, and then eventually there's enough of it in one spot that it holds itself together, and we call it a galaxy. So then just to the right of that, we have a spiral galaxy like our own Milky Way. And these galaxies they can be fairly young. They still have a lot of new stars being made. They're just happy chugging along. But occasionally the black holes at the centers can start feeding, and they can go into active phases. So that's the top image. There is another active galaxy where you can again see the jets shooting off from the supermassive black hole. And this kind of turns on and off. The black hole might start feeding, and then at some point later in time, it stops feeding again. Like we think that the Milky Way's supermassive black hole was actually feeding fairly recently, but then it turned off. So exactly how the supermassive black holes start eating and decide when they're finished eating is something that we're still trying to understand. So then the galaxies merge a lot. And as I mentioned before, eventually those mergers, all that gas and dust collides and makes a bunch of stars. And then the big blue stars die. So you're left with a red and dead elliptical galaxy on the very right-hand side. And eventually that's just going to keep going. Some of the red stars in there can live longer than the entire age of the universe so far. So it'll be around for a pretty long time, just sitting like that. So we can think of the different types of galaxies. We like to classify things. Humans like to classify things. So we like to put our galaxies into nice little bins. But the different types of galaxies are just galaxies at different ages, basically. So we have these spirals, which are younger, lenticular, which is just a fancy way of saying it's kind of in between a spiral and an elliptical, and ellipticals, and those are the main ones. We also have barge spirals. I should say the Milky Way is technically a barge spiral, and they're similar to spirals in that they're young, have a lot of blue stars, but exactly why the bar is there and how it's there is also an active, open question. And then we have things like irregular galaxies, which have just gotten, maybe they've collided with a much bigger galaxy that's just sort of tearing them apart, or maybe they've undergone so many mergers that they don't really have a well-defined shape, or maybe they're still collapsing and just haven't had enough time to reach that nice shape yet. And then we have all sorts of different types of active galaxies and radio galaxies and galaxies that are feeding and have all sorts of interesting things about them. But again, that's a different topic. So I've mentioned some open questions so far. There's a lot we don't know about galaxies and how they form. And so how do supermassive black holes form and grow? Some people think that, we know that when a really big star dies, it can form a black hole. And we call these stellar black holes because they're made by dying big stars. And is a supermassive black hole just the result of a bunch of these that ended up clumping together to form one really big black hole? Or do supermassive black holes somehow have some way of forming on their own? And do they have some way of becoming extremely big that's not related to just a normal star dying? So that's a question that we're trying to answer. The second one, kind of jargony. I won't really go into a lot of detail. How does the star formation exactly turn off? Like the mechanisms for that aren't very well known. There are questions that galaxies, especially merging galaxies, can tell us about dark matter. We can study how the gravity affects the different components of the galaxy or of galaxies when they're colliding, and this can tell us things about dark matter. We can also say, plug in a certain property of dark matter and then run a simulation and see if the simulation gives us something that looks like our real universe. How do the supermassive black holes start and stop feeding? I mentioned that. How did young galaxies affect the evolution of the entire universe? So this is also its own topic. There are things like AGN and stars that we think changed the chemical properties of the entire universe. That we call that reionization, if you want to ask more about that later. So I think that's most of what we have for the presentation. Now we can start answering some of your questions.
And we have a list of questions here. And so I'm going to read the questions and then Jamie and I will answer them.
So while sorry.
Go ahead.
While Laura's reading the questions, just a note on this picture. This is the Hubble Extreme Deep Field. So what they did is they took the Hubble Space Telescope, pointed it at what looked like an empty patch of sky, and just stared at that empty patch of sky for days and days on end. And then this is what popped out, is a bunch of super, super faint, super distant galaxies. Basically, everything in this picture is a galaxy. There are a couple stars in here. The ones with cross-shaped things on them are stars, but everything else is a galaxy. And the really faint smudges that you see here are galaxies essentially from the very beginning of the universe, because light takes time to travel over the universe. So the further we look back, the further we're looking back in time. And these are some of the oldest galaxies that we've ever been able to see.
Great. So our first question is from Raja, who asks, how do you get the pictures of the galaxies? Jamie, would you like to answer that one?
Yeah, so we use a variety of telescopes to get pictures of galaxies. We can't get a picture of our own Milky Way. Anyone who tries to show you a nice spiral-armed picture of our own Milky Way, definitely, yeah, that was definitely made by an artist or something, because we're inside our Milky Way. We can't see what it looks like from the outside because we can't travel that far. But other galaxies we can take pictures of with big telescopes and things like that. So the image on the title slide of this presentation, the Whirlpool Galaxy, was a Hubble Space Telescope image. So they just point the telescope at it and stare. But one complication is that telescopes look in certain frequency band. They look at certain colors, and the colors that are interesting for science aren't always necessarily the colors that look pretty when you print it in a picture. So oftentimes you'll see them use false color or synthesize multiple colors from one instrument into one image or something like that.
Great. Our next question is from Martin, who asks, this is a question about the two men who were debating whether the galaxies were nebulae or other galaxies. And he asks, how did these men theorize that the stars were in a spiral, and what exactly did they observe?
Yeah, so they actually didn't really know that the Milky Way was a spiral at this point in time. They just saw these other spiral things out in the universe and thought maybe the Milky Way could be one. But it actually took some more observations for us to figure out that the Milky Way was a spiral. But the observations they actually looked at, oh my gosh. Sorry, Google Slides just decided to kick me out of everything.
Jamie, is there a way I can
Sorry,
go back?
Okay, I got it. Okay. Sorry about that. So the actual data that they used, the information that they were drawing their conclusions on, Shapley, his evidence was a different astronomer, Adrian von Manen, made some observations of a galaxy called the Pinwheel Galaxy. And what Adrian von Manen thought he saw was the galaxy actually spinning over, the time that he was observing, which was, not hundreds of millions of years. When in reality, these galaxies take hundreds of millions of years to spin around once. So he thought he saw the galaxy spinning, but later he figured out that he didn't actually see that. But so one of Harlow Shapley's biggest pieces of evidence turned out to just be a bad observation, which, that's a problem. If you base assumptions and models on incorrect data or incorrect assumptions, then it can lead you down a wrong path and make you waste a lot of time. Heber Curtis was arguing based on the number of nova. So if we look at our Milky Way galaxy, we can count the number of nova, the number of little flares that go off in a given area, in a given volume, in some amount of time. And that should tell us, we just kind of guess that that's roughly the same everywhere, because why wouldn't it be? And when he looked at these distant spiral nebula, he observed that those nova would have to be happening way more frequently than they were in the Milky Way if it were inside the Milky Way. There would have to be something really weird about it. And that just didn't really sit right with him. He thought, if we just say that this galaxy is really, really big, then the number of nova are easily explained and consistent with the number in the Milky Way.
Martin also asks if we know how often a galaxy is formed in the known universe.
So not many galaxies are still forming today. And it's an interesting question, right? Because we don't know how much universe there is. There could be a galaxy forming. If you consider an infinite volume, then there is always a new galaxy forming. But maybe that's not true. Maybe galaxies all formed at the beginning. generally they formed very early on in the history of the universe, maybe like 8 to 10 billion years ago, and have mostly just been evolving since then. So we have less. We can only really talk about our observable universe, the bubble we can see, right? Because if you just if you have infinite stuff, then your numbers all go to infinity. So if we just consider what we know about, then there are a lot fewer galaxies forming right now than there were earlier on in the universe's history, just because all of this primordial gas and dust and stuff has already gone into making generations of galaxies and then gotten used up by becoming stars and things like that.
And Martin has one more question. He asks if we are showing real images or artists' conceptions. So Jamie, perhaps you just want to tell us which images we saw were actual images and which ones were not?
Sure. So I think the only artist's well, obviously Lord Ross's drawing from 1845 is an artist's impression because it's pretty obvious that that's a drawing. But other than that, only the supermassive black hole images. Slide 10, the two supermassive black holes spiraling towards each other. This slide, yeah. These two are artists' renditions, but everything else, I believe, is a real photograph or a real simulation. There's one simulation on the lifetime slide, but everything else are real photographs. Real pictures taken with telescopes.
And we have a question from John, who asks about the age of the Milky Way. He says, I thought the Milky Way was not much younger than the universe itself. Is that correct? If not, how can elliptical galaxies be much older?
Sure, I've been talking a lot. Do you want to take this one?
Sure. So galaxies, everything is rather old in our universe. And so basically what we're seeing with the galaxies is we're seeing a snapshot in time. And so we are seeing, a lot of it depends on the travel time of the light from the galaxy to us. And so if a galaxy is much, much, much farther away, then that light is taking a long time to get to us. And so we will see it in an earlier stage of its life than it might actually be in at that time. So that kind of influences how we're seeing the age of the galaxies. But in general, all galaxies are very old, and it's kind of a scale of everything being old and what is much, much older than old. Jamie, do you have something to add to that?
Yeah, just that when we call elliptical galaxies old, we're kind of being sloppy, because you're right that, maybe an elliptical galaxy was originally 3 spiral galaxies that all smashed into each other. And those spiral galaxies are galaxies probably mostly formed at the same time. There's probably, like I mentioned in the last question, there could be ones forming all the time, but most of it happened early on. So if we say an elliptical galaxy is older, it's a little bit sloppy. What we really mean is that it's more evolved. It's more mature, but not actually older.
All right. Another question from Martin, who asks, do galaxies spin or rotate? And you were talking about this a bit, Jamie, earlier with the pinwheel galaxy. Could you elaborate on that a bit?
Well, yes, is the short answer. But like I mentioned when I was talking about the pinwheel galaxy, it happens so slowly, so slowly that we would never really be able to tell on the, if you took a picture of a galaxy now and then waited until, waited 100 years and then got your grandchild to take another picture, they would probably look exactly the same. You'd have to wait 100 million years to actually see it rotate noticeably. But we can tell that galaxies are rotating because we can actually tell how fast things are moving in them. you might be familiar, if there's an ambulance driving towards you, it sounds higher pitched. And when it's driving away, it sounds lower pitched. It goes, and that's called the Doppler effect. The same thing happens to light. So what's happening with the ambulance is the sound waves are closer together because it's traveling towards you. And then they're further away when it's traveling away from you. And light does the same thing. So something moving towards us, the wavelength of the light is going to be compressed, which means it gets bluer. But if it's moving away from us, the wavelength of the light's more spread out, and so it gets redder, because that's all red and blue are, just longer and shorter wavelength light. So by looking at the distortions in the color over a galaxy, we can tell that this edge of the spiral is moving towards us, and this end is moving away from us. So it's pretty obvious that the galaxy is not splitting in half like that. It's probably just spinning. And we can see this for stars in our own Milky Way too.
So Martin's next question is about the galaxies themselves, if they travel through the universe and if we've measured how fast any of them are moving. And this question actually relates directly to what Jamie was just saying about the Doppler effect or redshift from individual stars and things inside a galaxy. We can also do this with galaxies as a whole, and we can tell whether the galaxy itself is coming towards us, going away from us, and how fast using that same method. We have a question from Ron, who asks, why do spiral galaxies have a spiral shape?
That's a great question. So that's something that we have ideas about, but we don't know that we've really totally pinned it down yet. So in general, the easiest shape for a collapsing blob of stuff to make is sort of a disk. This happens when you're forming new stars. You could see the disk around those black holes, and even though it was an artist's conception, that's pretty much what they do. So the pancake disk shape is pretty easy. It's only when you get a bunch of those, colliding at weird angles that it all gets jumbled up and becomes an elliptical. But, then the question is, how do you go from a disk shape to spiral arms? And that's sort of the big uncertainty. And we think that it has to do with the way that density waves are propagating and rotating. Trying to think of an easier way to explain this. Basically the rotation speed of every individual star is not exactly the same. So instead of every star rotating as one, there are sort of parts where where more stars, where they kind of you can think of them as getting slowed down. So they clump up in certain areas where there's just more stuff. And those areas where they start clumping start forming spiral arms. So it's just to do with the density of the stars as they're rotating. But exactly how this happens and some of the finer details we're still doing a lot of research to figure out things like that. But it's a great question.
Iavanti would like to know about the telescopes and if they are moving and how they stay still to take the images of the sky. So the way that the telescopes actually do this is that it's called tracking. They once you get your telescope set up, you basically calibrate it so that it has a sense of direction on the sky. You know what direction your sky is moving, and so your telescope actually just moves at the same speed and in the same direction as the object that you're trying to observe. And so you're basically, it's called tracking because that's what you're doing. You are tracking the object, be it a star or a galaxy or whatever you're observing, as you're moving across the sky. So you're holding still in relation to the object that you're looking at, but the telescope itself is moving. And again, that's just because the sky itself, well, it's actually us that's moving. But to us, it looks like the sky itself is moving. And so our telescope has to follow that.
And also, a lot of these things are so far away that like the fact that the Earth is rotating around the center of the Milky Way, and the Earth the sun's rotating around the center of the Milky Way and the Earth's rotating around the sun, for really distant galaxies, it doesn't really matter that much. It's like the parallax effect. When you're driving down a road, a distant mountain doesn't really appear to move very much, whereas if you go by a fence post that's right next to you, it's going to whiz by.
Our next question is from Martin, and he would like to know what is the known count of observed galaxies in the known universe? I believe it's around 10 to the 11. Is that correct, Jamie?
I'll believe you. I don't have a number for that off the top of my head.
That is what I've heard. So somewhere around 10 to the 11. Basically, a lot.
That's probably something that you could look to the literature for a more rigorously derived number.
Martin also asks, if we have to see through our galaxy to see other galaxies, then how many patches of sky have astronomers actually studied to date in order to look at the galaxies?
Yeah, that's a great point. So, if there are stars or gas dust clouds in front of stuff, it makes observing it really hard. And so there are limited areas of the sky where you can actually make those observations. So the telescope project that I work on, for example, is it basically looks out of the bottom of the galaxy, away from the galactic plane. So, if the galaxy it's a pancake from our perspective, right? So if we look up or look down, we can sort of avoid seeing most of it because we're not looking through the thickest part. We're just looking through, the top and bottom.
And we have a question from Aditya, who asks, if we can't see how big the Milky Way is, how can we say that it will take this many light years to travel across it?
So we can't just take a picture of the Milky Way and immediately know how big it is, but we actually have cleverer ways of figuring it out. So sort of the Doppler shift stuff I was talking about earlier. If we look at if we know the distances to a bunch of objects and we map out how fast they're moving, we can basically build a 3D map of our Milky Way, and we can figure out how big it is and look at Andromeda and figure out how fast we're moving relative to Andromeda and things like that. So early astronomers didn't have ways of doing that. And, the average person looking at the night sky with their telescope doesn't have an easy way of doing that. But if with, really nice fancy instruments and sophisticated analysis techniques, we can figure it out.
Paul asks, how many stars are in the Milky Way? And also, he would like to know how many galaxies we think there are in the universe. So we don't know how many galaxies there are in the universe because we don't know how big the universe is. But in the known universe, again, I think the number that I'm recalling is about 10 to the 11. And I'm remembering that because there are about 10 to the 11 stars in our own galaxy, and then about 10 to 11 galaxies in the known universe. Jamie, are those the numbers that you have? Because that's what I am remembering.
Yeah, so 10 to the 11th is 100 billion for those not versed in scientific notation.
Thank you. Yes, that is a good clarification. From Martin, we have a question. Do astronomers estimate the count of stars in a known galaxy?
Yeah, they can, if there's a reason to. Observations in astronomy have to be very well motivated because a lot of people are competing to get time on like a very small number of telescopes. So you have to have a really good argument for, we could point the Hubble Space Telescope at a galaxy and count how many stars there, but you have to convince the Hubble Space Telescope people that that's worth their time to do. So we can, it's just, can you convince the right people?
All right. How about we take one more question now, and then we will go on to our activity. And then once we get the activity underway a little bit, Jamie and I can come back and answer a few more questions. And then that should probably take us about our full hour. So our last question for now is from Iavanti, who says, how do we know that a galaxy was born close to the Big Bang or not?
That's a great question. Figuring out how old galaxies are is pretty difficult. So one of the easy ways that we can try to do this is look for the oldest stars in our galaxy. And there have actually been some points of confusion and crazy headlines because people find stars that they think are older than the whole universe, but now it turns out they just got the age of the star wrong. But yeah, looking for signs like that. We can look at, the compositions of like asteroids and stuff that have only been, or I guess that's more for our solar system, but the same principle applies. You can look at really old stuff, and if you figure out how old that old stuff is, then you can sort of tell how old the galaxy is. Do you have I'm sure that answer could be improved. Do you have anything to say?
No, that's about all that I would have said too. So I'm going to take us on then to our activity, and I will momentarily here be posting in the chat the link that we will be using. Again, this is the link for Galaxy Zoo, and so there, it should be in the chat now. And you can click on that link and follow along with us as we go through this if you'd like. So Galaxy Zoo, this is a citizen science project, and what that is that astronomers took a bunch of data, and they have all of these images of all of these different galaxies, and they need them classified. And there are a few complications with this. First of all, as Jamie was saying earlier, galaxies come in all sorts of shapes and sizes and dimensions, and there are some things that look exactly like a spiral galaxy and some that look quite irregular, and it's sometimes hard to classify exactly what you're looking at. Another challenge is distance. The farther away a galaxy is, the harder it is for us to tell exactly what it looks like. You want to zoom in on it, but we can't because we are so far away, and that's about the best image that we can get. So the astronomers took all of their data, these images, and they asked citizens, the public, everyone here listening to the call tonight, basically, to look at these and try to help them figure out if there's a way to classify them. So they've got certain classifications, and I'm just going to step you through a few steps in order to get you going as to how this actually works. So when you go to the Galaxy Zoo website, you want to first click on the Classic. There are two options there. You can go Classic or Enhanced. I suggest starting with the Classic because those galaxies are probably going to be easier to look at and see what you're doing. The enhanced ones are going to be the harder ones, which is great. If you want to do those, that's awesome. But I recommend doing at least one classic one first so that you know what you're doing. When you get there, when you click on that button, you will be shown a page that it's got a little tutorial that's pulled up for you, but I'm going to step you through it anyway. So you'll see something that looks relatively like what you're looking at on my screen right now. You will have an image of a galaxy on one side, and you will have a list of options on the other side. So this question is asking, is this picture of the galaxy, is it smooth? Or do you see some features in it? Or is it actually not a galaxy, but in fact like a star or something? And they'll always include these little kind of graphic images next to the descriptions to help you figure out, oh yeah, it looks like this, or oh, it actually looks more like this. So for this one, I see something here in the center, so I would click this features or disk option. However, this is just on my slideshow screen here, right? So I can't actually click this. But if I were on the website, that's the one I would be clicking, and then this bottom bar up here would give me the option to move on to the next question. And then that next question would be one of several things depending on what you chose. They'll ask things like, is there a bar? And you can see the examples here showing a bar inside a galaxy. And, they've got a few different pictures there. And if there is a bar, how strong or how weak it is. So you select the one that looks most like the galaxy that you've got an image of. And then the next question might be, is there a spiral arm pattern? Again, spiral arms are like, well, exactly what they sound like. These spiral arms that just kind of reach out there and spin around. Or is it just kind of flat or not spiral? So you'll select your choice there and go on. I should mention, don't worry too much about knowing whether you're right or not. There are lots and lots of people who look at these galaxies, and each galaxy is looked at several different times. And so they're basically trying to take an average poll of most people think this galaxy has a bar in it, or most people think that this galaxy has spiral arms, and that's how they're going to classify them. So if you just totally click the wrong button and click that, no, there are no spiral arms, when there definitely are, don't worry, because that would just be, one count in comparison to many others. So you're not going to mess anything up here. Just give it your best. Try to be honest, because the more honest you are, the more it helps the astronomers. But don't stress about, oh, I don't know exactly what this is. That's fine. They're just asking for your best guess on these things. Okay, so here are two examples of questions. You will get several more questions. I don't remember exactly how many there are right now, but there are lots as they try to identify different parts of these galaxies. And it'll kind of walk you through that. But there are a few other helpful things on this website. On the actual page itself. So one of them is this light dark feature. So your image of your galaxy, when it first comes up, will look something like this left image here. And then you'll see this little button there that I've put a red box around beneath the image. When you click on that button, it flips everything from a light color to a dark color and from a dark color to a light color, and you'll get the image that looks on the right. And this can be helpful in certain circumstances where you're trying to see a certain feature, as in, like here, if we were trying to study the center of that galaxy, and you're trying to figure out what exactly it looks like, if you change it from dark to light, or from light to dark, depending on how you're looking at it, you'll see it in a different way, and it might help you actually identify what's in there. So that's a helpful feature. We also have this lovely, oops, I went to a slide too far. There we go. We also have this lovely tutorial button. Whenever you click on that, the little tutorial will pop up, and it'll talk you through about basically the same thing that I'm saying right now. And so that's great. If you ever get stuck, you can click that, or you can also click the Need Some Help with This Task button. And that should also give you some help in terms of what you should be looking for that specific question. There's also a field guide on the side. You'll see that little field guide button there. If you click on it, it'll show you what questions you will be asked about this galaxy, and you can find where you are in that list. So as you can see, there are lots of questions here, but they come up and they're individual, and you can take them one at a time. And so this is just kind of a little bit of a guide to help you know, oh, I'm close to the end in classifying this galaxy or not. And again, that's on the side. If you click on it, it'll pop up, and if you click again, it'll go away, but it's not automatically open. And is there anything else? I think that is my last slide. So again, that link is in the chat, and you can click on that and you can start working through these galaxies. Please ask questions in the chat if you are having trouble finding this, don't know where you are, or something, having any difficulties. Let us know, and we are happy to help you get going on that. Jamie, is there anything else you'd like to add about this before we go back to some questions?
Yeah, thanks for that. Just hopefully after seeing that presentation, you all have a little better of an idea of what all of these different looking galaxies, why they look different, where they are in their evolution. So in the olden days, astronomers would just, they only had images of a few galaxies, so they would go through them by hand. But nowadays, we have these awesome surveys, like the images you see here were taken with the dark energy camera. which is at an observatory in the Atacama Desert in Chile. And it just scans huge regions of the sky with a really wide field of view. So it sees a lot of sky at once. It doesn't focus in narrowly, but it just tries to get as much information about a big piece of sky as possible so it can get images of all of these galaxies. And then the result is our telescope's so awesome that we get more galaxies than we can actually look at. So we have to crowdsource doing that. But classifying these galaxies can tell us things about how the mergers affect their evolutions, how the host environments affect how they form and merge and evolve, and all sorts of interesting questions. So if you go to the About page on the Galaxy Zoo, which I think is on the right-hand side of the main page, you can read a little more about exactly what the science goals there are that I just outlined.
Great. Jamie, how about we take a few more questions in our last few minutes? Does that sound good to you?
Sounds great.
Okay. So from Gary, Gary asks, what would happen to the black holes when two galaxies merge? And I think this harkens back to Jamie's talk about the supermassive black holes and the spiraling in when they start to merge. Basically, if you have two black holes at centers of galaxies, when those galaxies merge, the black holes will be pulled towards each other due to gravity, and eventually, a long time in the future, they will eventually spiral in and merge together. It won't happen immediately. It's kind of part of the whole process, but that will happen. Jamie, is there anything else to add with that?
Just an interesting way to visualize this is that galaxies aren't all rotating around the supermassive black holes. The supermassive black holes are just heavy stuff sinks to the bottom, but there's not a bottom of a galaxy. Well, it depends on which direction you're looking at it, but the heavy stuff sinks to the middle. So eventually the two supermassive black holes, when galaxies are merging, they'll sink to the middle of this new conglomeration of galaxies, and where they'll merge, like Laura said.
Our next question is from Martin, who asks, do galaxies have poles comparable to north and south poles formed by magnetic fields?
Yes is the short answer. The slightly less short answer is that their magnetic fields are really interesting and complicated. The Earth's magnetic field, I think, I'm not an expert on the Earth's magnetic field, so take the statement with a grain of salt, but I think it's fairly well understood exactly, its dynamics and why it's there and what it looks like. But the magnetic field of the Milky Way is a really big thing, and a lot of interesting stuff is going on inside it. So its magnetic field is affected by, past mergers with other galaxies. Oh, something I should mention that I forgot to when I was talking about mergers is that the Milky Way is actually merging with some other small satellite galaxies right now. And obviously we don't notice very much, but things like that can disrupt and affect the galactic magnetic field. So galaxies do have very relevant magnetic fields, and they can be very complicated in their structure, more so than just simple poles like for the Earth. But yeah.
All right. Angie asks, how soon after galaxies form do stars form?
This is a really good question, and I don't know that there is an actual answer, because how the first stars formed and how the first galaxies formed is something that we're still trying to kind of pin down exactly. So we think they formed at vaguely the same time, maybe galaxies a little later. I don't know. Do you have anything to add, Laura?
I don't. I was hoping you'd have some more information on it. So Angie, great question, and ask us that question again in another 5-10 years or so when maybe someone's found out something more. Or you can go read the literature yourself, and perhaps you'll find out that someone has figured out something. We have, maybe, Jamie, we've got about 3 questions left. Would you be okay staying on just to answer the last 3 questions?
Yeah, sure.
Okay. So from Ron, we have a question. If we could explain simply how the magnitude of the galaxy's mass at the center causes the spiral. He's wondering if it's a space-time shape. Do the center's mass cause a wave of stars in the spiral arms?
So exactly how the centers of a galaxy affect the dynamics of the galaxy is something that's not totally clear. People they've historically thought that they've found relationships between, like the supermassive black hole and the presence of spiral arms or rotation speed or something. But a lot of those claims are sort of dubious. It's not really clear exactly how much they're related, but that's another open question. So another good one.
Martin has a very specific question for us. He asks, what are the 3 most important questions that astronomers are asking at this time? And that sounds like kind of an opinion question. So, Jamie, you want to give us your opinion about the 3 most important questions?
Yeah, sure. Let me just... So I have 2 that immediately spring to mind. Are these... do these have to be astronomer specific? Some of mine verge into physics.
Well, it says astronomers,
Okay.
but I don't know. Perhaps physics would be okay too?
Well, yeah. So I guess I'll start with the ones that immediately jump to mind. So big one is the Hubble constant tension. So the Hubble constant is, taking a step back, our universe is expanding. It's expanding like the surface of a balloon if you blew it up. Like every 2 points are just becoming further away from they're becoming further away from each other. So every point is becoming further away from every other point. And it's not expanding into anything. There's just becoming more space between things. And this doesn't, gravity can win over this. That's why the Milky Way is not flying apart. But if we look at really distant out galaxies, then we see that they're all traveling away from us. Well, it looks like they're all traveling away from us because the universe is expanding. And the Hubble constant, named after Edwin Hubble, who's the person who discovered that the universe was expanding, and who the telescope's named after. The Hubble constant is kind of just a number that tells us how fast the universe is expanding. Which should, it seems like a pretty straightforward question, right? We see that the universe is expanding. We should just go measure how fast it is. One of the problems with this is, like I said, measuring distances in astronomy. So we can measure how something is redshifted, how fast it looks like it's moving away from us. But then in order to actually figure out how far away it is independently, so we can match those 2 things up to figure out the speed, then we need some way of figuring out the distance. And we use things like there are certain types of supernova that always go off with the same bright, or you can always figure out how bright they were after the fact, because they have a similar physical mechanism that's driving them. So we call things like that standard candles. We know how bright they are. So if we see one happen in a galaxy far off, we see how bright it is, and that can tell us how far away the galaxy is. But this is subject to all sorts of problems with, like, how do you calibrate your standard candles and things like this. And these are also taking a measurement of our local universe. They're looking at galaxies, looking at supernova, looking at certain variable types of stars to make these measurements. But there are other independent measurements of the Hubble constant that come from the very early universe. So looking at the cosmic microwave background, the thing I study, which is the afterglow of the Big Bang, we can get a totally separate, totally independent number for not how fast is the universe expanding now, but how fast was the universe expanding 14 billion years ago. And we get a slightly different answer. Not dramatically different, but slightly different, like 73 plus or minus 2 versus 67 plus or minus 2 or something like that. So pretty close to each other, but given how good the measurements have gotten, it's enough to get people worried. So, there are different camps that people fall into. Maybe, some CMB people might be inclined to say that there's just a systematic problem with the local measurements. And maybe the local people might just say, Well, the local people have kind of run out of excuses for accusing the CMB people of errors. So now they've turned to, oh, well, it's new physics, which it could be. I'm obviously showing my bias here, but I think this is an opinion question, so I have some license to do that. But note that there is opinion here. It could be new physics. It could be that our model of cosmology that, we have to plug in, this number relies on some assumptions of how the universe works. And maybe some of those assumptions are just wrong. That would be the coolest and most interesting answer. Yeah, so that's one big issue, is the difference between early universe and late universe measurements of how fast the universe is expanding, the Hubble constant. Number two, I guess, wait, do we want to alternate? I've been talking for a while, and that way we won't influence each other quite as much.
So my next big question that I'd put out there, and again, this is my opinion, and it's probably biased because this is kind of along the lines of what I'm studying, but I personally think that we need to understand galaxies a lot better than we do, because we have lots of galaxies and we're in one, and while we know a fair amount about them, we really don't understand them all that well. And so I'd say one of the questions, I agree with the Hubble constant question that Jamie was talking about, and the second question that I would say is very important is just exactly how do spiral galaxies work, or exactly how do galaxies in general work, and I guess trying to iron out all of those details. And there are a lot of questions that are kind of summed up in there, so perhaps that's kind of a sneaky way for me to slip in, like, 25 questions or something under the umbrella of one question. But yeah, I would say the second question would be understanding more about galaxies, to understand more about our home as the Milky Way.
So for my number two, I guess my internal bias would want me to say inflation, but I'll save that for number three, because probably the biggest question that we're trying to figure out, and these aren't being ranked in order, they're just as I think of them, but what I would state is the biggest question, and it's kind of two, I'll say 2A and 2B, are dark matter and dark energy. So these dark things are placeholder explanations, basically, for, we see that there's extra mass in this galaxy. So for example, there have been observations of the Bullet cluster, merging cluster of galaxies, where we can measure where the mass is based on something called gravitational lensing, where the gravity from the galaxies bends light from background galaxies. Just like a lens bends the light, the lens in a telescope or in eyeglasses bends light, gravity can do the same thing. And more mass bends it more, so we can figure out how much mass there was. But if we just add up all the stars and gas and dust, there's not enough. And it's not, it's not just like a 10% difference. It's like a factor of 10. There should be 10 times more stuff than we're seeing. So something's wrong. And we have some other ways, like the microwave background, again, loves to provide independent measurements of things that tell us that we need some sort of dark matter, some sort of, it's heavy, it's like matter, it clumps up under gravity, but it doesn't interact with light as far as we can tell. And we're not sure exactly what it is on like a particle level. It's not there in the standard model of particle physics. And then dark energy has a very similar name and really deserves its own spot, but I really want to talk about inflation as number three, so I'm just clumping it in here. Dark energy is completely different from dark matter, except that we also don't understand it very well. So I mentioned that the universe is expanding, but the universe is filled with stuff. There are galaxies. And eventually, all the gravity of that stuff should cause the universe to start, to slow down in its expansion and then start coming back together. So for decades, people just assumed that this is what we would see, that the expansion, if we measured the acceleration of the expansion, we would find that it was either, staying about the same speed, we couldn't really tell, or that it would be slowing down a bit. But Instead, we saw the complete opposite. We saw that the expansion of the universe is speeding up, that the universe is expanding faster and faster as it goes forward in time. And this was a complete shock. This was the, I believe, 1998 Nobel Prize in physics. And I think is, one of the big, we haven't had any big surprises in physics in a long time, not since really the development of the standard model of particle physics in the 60s and 70s. It's usually been that the theory is ahead of the experiment, that people come up with a bunch of explanations and then have to go do experiments to figure out which explanation is correct. But the most exciting things in science are the opposite, where we just find something that nobody predicted. And, that doesn't happen as often anymore because we know a lot by now. But it just makes it that much more exciting when it does happen. So figuring out that the universe was accelerating in its expansion was just earth-shattering. And dark energy is, at its base level, we talk about it as kind of an intrinsic energy that space has. And it exerts a negative pressure, basically, that some empty volume of space will exert a negative pressure that causes it to expand, to start expanding faster. So yeah, that's my very, very bare bones synopsis of dark energy. But dark matter and dark energy are together make up like 80% or like 90% of the universe that we live in, as far as energy content goes, and yet we have no really idea what they are. We can study their properties and their dynamics, but they're still pretty big mysteries.
So that would take me to my third question, and that's because my first question was the same as Jamie's with the Hubble constant, and then the second one was galaxies. So the third one, I actually would focus on dark energy, and only dark energy. I would personally skip the dark matter, and that's because while we don't know everything about dark matter, there's a whole lot more we need to learn. We kind of know its effect, and we can kind of see what it's doing. And so, yeah, it would be great to understand it in every single detail. But to me, the bigger problem is dark energy because we kind of have no clue about that. And so I feel that that's more pressing, going to lead to, shall we say, bigger insights into our universe if we can figure out something more about dark energy. So I would list that as my third important question in our list of three. And again, these might not exactly be in order, although mine, for me, actually are in my personal interest order as to what's most important and what's not.
I guess that brings me to number three then, where I have to represent my own personal interests and say inflation. So our basic model of the universe, which we call lambda CDM, if you want to look that up on your own, but I won't explain what all that means right now. It has some holes in it. It has some things that it doesn't explain, and some weird inconsistencies that we have to find a different explanation for. So one of those we call the horizon problem. So we're being bathed in this glow from the Big Bang we call the cosmic microwave background. And the light that's reaching us from the cosmic microwave background is just now, so there was a moment in time where the universe became transparent, basically. It underwent a phase transition and became transparent. But the point is just that all of the light from the CMB was released at about the same time. It became transparent, so the light, the afterglow, could just go through the universe and not get absorbed by anything. So when we're getting that light now, this is light that was released 380,000 years after the Big Bang, basically 14 billion years ago, right at the beginning of the universe. But there's kind of a problem with that, which is that we see that the microwave background is almost exactly the same temperature everywhere. So the patch of sky all the way over here, whose light is only now reaching me since the beginning of the universe, and the light from all the way over there that's only now reaching me since the beginning of the universe, were from things that were the same temperature. And that seems a bit weird. Why would they be exactly the same temperature? Unless there was some mechanism forcing to be, or maybe, well, so the answer to this and some other questions is an idea called inflation, which basically posits that the universe underwent this extremely rapid exponential expansion right at the very beginning. That then, that phase ended and went into the normal, what we call Hubble expansion that came after. And, after the end of inflation is that's when the first atoms form and things like that. So this is 10 to the minus 35 seconds, incomprehensibly small amount of time after the Big Bang. If you even believe that it makes sense to define the Big Bang as a single moment in time, which is something one can argue. But very, very early in the universe's history, it expanded so fast that areas that were next to each other got blown up out of what we call causal contact. They're now so far away that it seems like they could never have communicated. But that's just because we weren't accounting for a super fast period of expansion at the beginning. And if we take that into account, then they could be at the same temperature. Maybe that whatever was inflating was not all at the same temperature, but it just expanded so much that some little spot that was about the same temperature became bigger than our entire observable universe. And the theory of inflation also has a lot more interesting and fundamental predictions. So basically, it's kind of the story of the beginning of the universe, that there were these tiny little quantum fluctuations in the vacuum. There are quantum fluctuations happening everywhere all the time, essentially. You can think of them as like people say particles popping in and out of existence, which is like one of those statements that's kind of right, but you shouldn't look at too closely because it's not really technically right. But you can think of it like that. And that then inflation happens, and these tiny little, it's slightly hotter in this spot, slightly colder in this spot, that gets blown up onto, cosmic scales. And then those cold spots, stuff starts to clump there. And that stuff eventually becomes galaxies and galaxy clusters and planets and people. So the theory of inflation sort of sets the seeds for the formation of all of the structure in our universe. But having explained what inflation is, we don't actually know for sure that it happened. There's a lot of really, what I would argue is really compelling evidence. But what would kind of be the smoking gun is the signature of these primordial gravitational waves from inflation. So if inflation happened, a lot of models predict that it would create this background of gravitational waves, ripples in the fabric of space and time. And these would be so weak now that we would need an instrument the size of the solar system to try to measure them, which people are trying to build in like 20 years. Stay tuned for that. But right now, we can look back to, they've gotten weaker as the universe has expanded. So we can look back to a time when they were stronger, which is when the microwave background was formed. And they've actually, if they exist, they might have left this imprint in the microwave background that we can measure. So that's what my group is actually working on, trying to measure the microwave background to find these signatures from the beginning of time. We haven't found them yet, but we're working on it.
Great. Okay. So those should be some important / exciting questions that astronomers are asking.
Yeah, Jamie, that was a great question. Thanks for giving us license to talk about things we wanted to talk about.
Yeah, great. Thank you, Martin, for asking that. Jamie, we have one more question, and then we should probably wrap up soon. So Our last question is from Gary, who asks, why do some galaxies have arms and others do not? And this goes back to what Jamie was talking about with the galaxy mergers, in that young galaxies tend to be spiral galaxies, and they have those beautiful spiral arms. Sometimes 2, sometimes 5, sometimes whatever, and that's again something that we don't quite know all the details about that yet. But then galaxies, as they mature, they collide with one another, they merge, and they become less and less spiral-like and more just kind of blobs. as the spiral arms get disrupted through the mergers. And so they become more and more just elliptical galaxies. And that's then when we see the red elliptical galaxies being our older or more mature galaxies. So basically the difference there is that we're looking at an evolution process where we have some arms and then they start to go away as mergers happen. Jamie, do you have anything to add?
No, that was a great explanation. Just refer you to our previous answer for the formation of spiral arms, which the long and short of it is that it has something to do with how the stars clump up in density waves, but the real answer is that we don't quite know. So I think, Laura, your first point about knowing more about galaxies is a great one, particularly because there have been so many times throughout this presentation that we've had to say, oh, well, that's a great question, but we're still trying to figure it out. So I think it's
stay tuned for when we actually figure out all of those questions.
Yeah, and these are great questions that you're asking us in the chat because they are relevant questions that we are asking ourselves and trying to figure out.
Wonderful. Well, I think that brings us to the end of our Universe at Home for this evening. Just as a reminder, there will be another Universe at Home next week, and another one after that for the rest of August, I believe. Is that correct, Jamie?
Yes, I think.
So I think we go through the end of August. Well, anyway, we go on for a few more weeks yet. So tune in again, and you can find the schedule and all of that information, same place where you found all of this information, and that would be through the MIFA website, Minnesota Institute for Astrophysics. So it was great to have you all here. Thank you for joining us, and we hope that you tune in again for some more presentations.
Yeah, thank you so much. Hope people learned some things and we had a good time. So tune in again.